In today's class, we are going to discuss about EMF equation of a transformer, losses in the transformer, what is meant by efficiency, condition for maximum efficiency. First, we'll study about the EMF equation of a transformer. So, to find out the EMF equation of a transformer, we have to consider a transformer having N1 number of primary turns. That is, N1 is equal to number of turns in primary. N2 is number of turns in the secondary winding. Phi maximum is maximum value of flux in the core linking both the windings, which is taken in Webers. Phi maximum is equal to Bm into A, where Bm is maximum flux density, area is A cross-sectional area of the given core. F is frequency of the supply in hertz. T is the time period of the sine wave of the supply, where T is equal to 1 by F. So when we are finding out the EMF equation of a transformer, consider a sinusoidal waveform. So the flux, whatever is flowing in the core, it will vary sinusoidally as shown in the figure. Why it is sinusoidal? It is because of alternating in nature. Since it is alternating in the nature, the flux in the core which will be varying is sinusoidal as shown in the figure. The flux, whatever is flowing, which is considered as sinusoidal, it rises to its maximum value, that is phi maximum, from 0 in 1/4 of the cycle, that is t by 4 seconds. It can be seen here, one complete cycle is t seconds. So to reach the half of the positive value, that is up to 180 degree, it takes t by 2 seconds. But to reach the maximum value, it takes t by 4 seconds. So the t by 4 second is nothing but which is equal to 1 by 4f seconds. So according to Faraday's law of electromagnetic induction, average rate of flux change, when we consider electromagnetic induction, Faraday's law, average rate of flux change is given by d phi by dt. That is rate of change of flux with respect to time, which is equal to d phi, means it is the phi maximum value. Since we have considered only t by 4 seconds, d phi will be phi maximum, which is divided by dt value, that is the time taken will be 1 by 4f. So if we simplify and write, it will be 4 into f phi maximum. This is average EMF induced per turn. So here the EMF which is induced per turn is average rate of change of flux into 1. Why it is taken as 1 is, we know that EMF induced per turn is n into d phi by dt. Therefore, here per turn, therefore n value will be 1 and rate of change of flux change will be 4 into f phi maximum. Therefore, so average EMF induced per turn will be 4f phi maximum. Since the flux is varying sinusoidally, the RMS value of induced EMF is obtained by multiplying average value by form factor. We know that RMS value of any alternating value is given by form factor into average value. Therefore, RMS value of induced EMF per turn will be equal to form factor into average value. Form factor is a constant value, we all know. It is the ratio of RMS by average value. Therefore, it is 1.11 into 4 phi f maximum. F phi maximum. RMS value of EMF per turn will be 4.44 f phi maximum volts. This is the EMF per turn. But the RMS value of induced EMF in whole primary winding, if you consider for the whole primary winding, it is represented by capital E1, which is equal to RMS value of EMF per turn into number of turns in primary winding. So E1 will be 4.44 f phi maximum N1. Similarly, the RMS value of induced EMF in entire secondary winding, with respect to the secondary, it will be E2, which is equal to 4.44 f phi maximum N2. So for ideal transformer, that is, these are the two EMF equations, that is E1 is equal to 4.44 f phi maximum N1, E2 is equal to 4.44 f phi maximum N2. For ideal transformer on no load, E1 will be equal to V1. That is, when there is no load applied, we know the condition E1 will be equal to V1 and E2 will be equal to V2, where V1 is the supply voltage, V2 is the terminal voltage, E1 is the primary induced EMF, E2 is the secondary induced EMF. So if in this EMF equation, if N2 is greater than N1, that is the number of turns on the secondary is greater than or more than the number of turns in the primary, the transformation ratio K will be greater than 1. Then this type of transformer is called as step-up transformer. So whenever it is a step up transformer, N2 will be greater than N1. If the transformation ratio K is less than 1, that is N1 is greater than N2, that is the number of turns in the primary winding is more than the number of turns in the secondary winding, then these type of transformers are called as step down transformers, where K is the voltage transformation ratio. So whatever is the EMF which is induced in the transformer, either it is with respect to primary or the secondary side, it is derived or it is applied by the equations E1 is equal to 4.44 F5 maximum N2 and E2 equal to 4.44 F5 maximum N2. So after we study the EMF equation, coming to losses in a transformer. So what are these losses means? In any electrical machine, we define loss as the difference between input power and the output power. So whatever the supply power is there and whatever is the output power we get obtained, when the difference is taken between those two, that difference whatever we get there, that is known as the loss in any electrical machines. So the transformer operates at higher efficiency when compared with other electrical equipments because of the absence of mechanical losses. Why there is absence of mechanical losses? We know that transformer is a static machine. Therefore, it operates at a very higher efficiency because of the absence of mechanical losses when compared with other equipments like DC machines, AC machines, etc. So here, when we talk about the losses in transformer, it consists of only electrical losses. Mechanical losses will be absent. So these losses are classified into two different types. First one is core loss or iron loss or constant loss. The second one is copper loss or the variable losses. When we say core loss or the iron loss or the constant loss, why is it given the name as core losses? Means it occurs in the core of the given transformer. So the ferromagnetic material of which is the core, which is made up of a ferromagnetic material, there whatever is the losses which is obtained or which is occurred, those are known as the core losses. So this iron losses or the core losses are caused by the alternating flux in the core of the transformer. So whatever is the alternating flux which flows in the core of a transformer, that causes the iron losses. As this losses occur in the core, the name is given as core losses. So it is further divided into hysteresis and eddy current losses. So when we talk about the core losses or iron losses, why it is known as constant losses? Because it does not vary. Once we get the core losses, it always remains the same. Therefore, it is given a name as constant losses also. So it is divided into two types, eddy current losses and the hysteresis losses. So talking about hysteresis losses, it is denoted by WH, W suffix H. The flux in the core is alternating. So we know that the flux which is flowing in the core is alternating. So the power which is required for the continuous reversal of the molecules of which the core is composed, this power is dissipated in the form of heat and it is called as hysteresis losses. So as the flux which is flowing in the core is alternating, to make this alternating flux flow in the core, what happens is the molecules which are present in the core has to be reversed. So that composition has to be reversed. To get it in a reverse composition, there will be some amount of power which is consumed. This amount of power which is consumed is not a useful one, which is dissipated in the form of heat, which is known as the hysteresis losses. These hysteresis losses always depends upon the flux density in the core and the supply frequency. Therefore, the hysteresis losses is given by WH directly proportional to B maximum 1.6 into F, or WH is equal to KH B maximum to the power of 1.6 into F, where KH represents the hysteresis constant which depends upon the material, F supply frequency, B maximum is maximum or peak value of the flux density. So we have to select a material such a way that always this hysteresis constant is very less, such a way the material will be very efficient or it will give a lesser losses and high efficient machine it will become. Therefore, when we consider selection of the material, hysteresis losses has to be taken into consideration. Talking about the second component of the iron loss or the core loss, it is eddy current losses. So what is this exactly eddy current losses is? It is nothing but when the flux links with a closed circuit. Means the transformer, when we consider we have two windings, primary and the secondary, it becomes a closed circuit. So when the flux which is flowing in the core links the closed circuit, an EMF will be induced in the circuit and the current starts flowing. Once the EMF is induced, the current starts flowing. This value of current always depends upon the amount of EMF around the circuit and the resistance. So that EMF, whatever is flowing, it always depends upon the how much is the amount of EMF which is present in the circuit and also the resistance of a given circuit. Since the core is made up of conducting material, this EMF circulates current within the body of the material. Therefore, what happens is it depends upon the EMF and the resistance. Because of the core which is made up of a ferromagnetic material, that is a conducting material, always these EMFs circulates current within the body of the material. Within the core itself, there will be a circulating current which will be flowing. These circulating currents are known as the eddy current losses. Since this eddy current losses, whatever is occurring, it is due to the experience in the it is due to the changing magnetic field which is experienced by the conductors. These are not responsible for doing any useful work, and it produces a loss in the magnetic material. So this loss, whatever is produced, is known as the eddy current losses. Eddy current losses can be minimized by establishing high resistance path using thin laminations. By making the laminations as thin as possible, high resistance path will be there. So if what is meant by high resistance, the property of resistance is to oppose the current. So if it has a value of very high resistance, it will oppose the current which is flowing that is the eddy currents, excess current, whatever is there due to the magnetic circulation, whatever is the current which is flowing, it will be resistant or it will be stopped. That is why we have to use a thin lamination so that eddy current losses can be minimized. So this eddy current losses is given by WE directly proportional to BM square F square T square. Because it involves the resistance and current values, all the values are taken in square. So WE is equal to KE into BM square F square T square, where KE is nothing but coefficient of eddy current. B maximum is maximum value of flux density, which is given by Weber per meter square, and T is thickness of lamination in meters. F is frequency of reversal of magnetic field in hertz. Therefore, the iron loss is given by sum of hysteresis loss plus eddy current losses. Since the core, whatever is taken to make the material which is taken to make the core, it always remains the same. Once the material is fixed, the core losses also will be fixed. It does not change. Therefore, these core losses or iron losses are also known as the constant losses. And the second loss is copper loss or the ohmic loss or the variable loss. So where do we get this copper loss or ohmic loss or the variable losses? These losses occur due to the ohmic resistance of the transformer windings. So because of the resistance present in the transformer windings, that is both primary and the secondary, copper losses are occurring. So this copper losses is always the I square R losses. Why? Because the power equation is given by V into I. But if we consider the windings, there we have a resistance which is coming into picture. So when we express the power as in terms of the resistance, it becomes VI will be I square R. That is why always copper loss is the I square R losses which is considered. So here the copper loss, when does the copper loss occur? We have two conditions where the copper loss will be occurring. One is under no load condition and one more is under the loaded condition. So what is the no load condition? That is in the secondary side when there is no load connected. What happens is, because there is no load connected, there will be no current which is flowing. There will be no EMF which is there. So since the no current is flowing, only copper losses will be occurring in the primary side, because the secondary side there is no current flowing. Therefore, when there is no secondary copper losses occurring, only across the primary the copper losses are occurring. Because of no load condition, the current consumed by the primary also will be very less. So copper losses will be very small and it is neglected. But once we make it a loaded condition or the load is increased, the copper losses become quite considerable. That is, under the loaded conditions, copper losses will be increasing, or it will be quite considerable amount which will be obtained. Therefore, under the loaded conditions, copper losses always occur in both primary and secondary windings. If I1 and I2 are the primary and the secondary currents, then R1 and R2 are the resistance of primary and secondary windings. So the copper loss occurring in both primary and secondary windings will be I1 square R1 and I2 square R2 respectively, where I1 square is the current which is flowing in the primary circuit, R1 is the resistance of primary winding, and I2 will be the current flowing in the secondary circuit, and the R2 will be the resistance of the secondary winding. So total copper losses of any given transformer will be sum of copper losses in the primary and copper losses in the secondary. So WCU is the representation of the copper losses, which is equal to I1 square R1 plus I2 square R2. These losses are varied according to the load, and hence it is given a name as variable losses. The other name of copper loss is variable losses. Why it is known as variable losses is, it is because this losses, whatever is the I1 square R1 and I2 square R2, as they vary the value of load, the current value also varies. Since the current value varies, the losses also will be variable then. Hence, it is given a name as variable losses. So, together the losses, total losses in a transformer is always given by WO, which is equal to WI plus WCU. So, this is the one representation, one form of representation which can be used. That is, WO is equal to WI plus WCU. The other type of representation which can be taken also can be taken as P is equal to Pi plus PCU. That is, P will be the total power loss, which is equal to Pi will be total iron loss and PCU will be total copper loss. That is one form of representation. Or else the other form is the W is equal to Wi plus WCU. This is the one form of representation which can be considered. So this is about the losses in the given transformer. So after we study the losses, we need to know about the efficiency of a given transformer. So this efficiency is nothing but, what is meant by efficiency? It is nothing but, in any transformer, if you take the ratio of output power by input power at any load and power factor, it is defined as efficiency. Or in general, if you talk about any electrical machine, the efficiency is always given by the ratio of output power by input power. So here, when we talk about the transformer specifically, what happens is efficiency plays a very important. Talk about efficiency, the value of efficiency for transformer specifically, it will be always above 90% or above. This is the ideal efficiency which can be obtained in the transformers. So here, according to the equation, efficiency is given as eta, which is equal to output power by input power. So it is a ratio of output power by input power. So this output power and input power can be expressed in terms of either the input or the outputs. So the output power can be expressed in terms of input power and losses. How it is means, it is given by output power is equal to input power minus losses, or input power can be expressed in terms of output power and losses. Therefore, input power will be output power plus losses. So what is losses? It is nothing but input power minus output power. So by considering this equation, either you can express output power in terms of input power or input power in terms of the output power. So the efficiency can be written as output power by output power plus losses, or it might be input power by input power plus losses also. Since this power, when I talk about the power, what is the power in a single phase AC? It is always VI cos phi. Since we are talking about the output power, that is the secondary side, efficiency is given as V2 I2 cos phi 2 divided by output power, again here will be V2 I2 cos phi 2 plus WI plus I1 square R1 plus I2 square R2. This WI plus I1 square R1 plus I2 square R2 are nothing but the losses. So this is the equation to find out the efficiency. This efficiency can also be obtained as efficiency, that is eta is equal to input power minus losses by input power. So this is expressing the whole efficiency in terms of input power. So here what will be the equation? It will be input power means V1 I1 cos phi 1 minus of Wi plus I1 square R1 plus I2 square R2 divided by V1 I1 cos phi 1. That is the equation. So either using the efficiency equation in terms of output power or efficiency equation in terms of input power, efficiency can be obtained. Transformer when it will be maximum. What is the maximum value which can be obtained? If you want a maximum value, at what condition it can be obtained? So to find out this, there is a derivation. So how do we do the derivation is consider the efficiency equation, that is eta is equal to input minus losses by input. That is, I'm considering the efficiency equation which is expressed in terms of input power. That is input power minus losses by input power. So this copper loss, when so here we have a losses which is given. This losses are iron loss and the copper loss. So the copper losses is WCU, which is equal to I1 square R1 or I2 square R2. And iron loss is given by summation of hysteresis losses plus eddy current losses. So when I substitute all these values in the equation, that is eta will be equal to input power. What is the value for input power? That is with respect to primary winding V1 I1 cos phi 1 minus losses. This losses, whatever we are considering, I am considering only with respect to primary winding. Therefore, it will be I1 square R1 minus WI, that is iron loss, divided by V1 I1 cos phi 1. Here, minus losses is there. Minus of iron loss plus copper loss, if I put, substitute and multiply the negative value with respect in negative value into the losses, I'll get it as minus I1 square R1 minus WI divided by V1 I1 cos phi 1. So the efficiency equation, when it is simplified, eta will be 1. How is this one? V1 I1 cos phi 1 divided by V1 I1 cos phi 1. It will be 1 minus I1 square R1 by V1 I1 cos phi 1. I1 square I will get cancelled. It will be I1 R1 by V1 cos phi 1 minus WI divided by VI cos phi 1. So this is their equation 1. So the efficiency is maximum for a given power factor when this equation 1 is differentiated with respect to I1 and equated to 0. That is d eta by di1 is equal to 0. If this condition, the condition for maximum efficiency is this d eta divided by di1, which is equal to 0. So now consider the equation 1 and differentiate with respect to I1. Therefore, what will be the output? With d eta divided by di1 will be equal to differentiation of 1 with respect to I will be 0 because it is a constant, minus R1 by V1 cos phi 1 is a constant. Differentiation of di1 with respect to di1 will be 1 plus. Why it has become plus? Because here I1 is in denominator. If I differentiate this I1 with respect to the which is given in the denominator, that is 1 by I1, it will become as minus of minus WI divided by V1 I1 square cos phi 1. Therefore, this will become plus. So this is the equation. Plus V. So d eta divided by di1 will be 0 minus R1 V1 cos phi 1 plus WI by V1 I1 square cos phi 1, which is equated to 0. So if this equation is simplified, I'm going to get it as WI is equal to I1 square R1. That is, iron loss is equal to copper loss. Hence, the transformer operates at maximum efficiency when we have iron loss is equal to copper loss. When the losses in the winding is equal to the losses in the core, the transformer will be operating at a maximum value of efficiency. So this is always important. Whenever a condition for maximum efficiency is asked, it is Wi will be equal to WCU. So we know that maximum efficiency is obtained. So to obtain this maximum efficiency, what should be our output kVA? That is the output whatever is obtained. What is that max output obtained when we have a maximum efficiency? That is what we are going to study next. So here, before we get to know that what is the output kVA corresponding to maximum efficiency, we should know what is kVA. kVA is nothing but kilovolt amperes. So when we talk about transformers, we always talk about the power. So what is the power equation? It is VI cos phi. What is VI? Voltage into current. And cos phi. Cos phi is power factor which does not have any units, but voltage into current is volts into ampere. So always when we talk about transformers, it is always volt amperes which is taken into consideration. Here, because the transformers are not always the smaller values, it is for the higher values which is taken, the ratings. That is why you always express the power of a given transformer in terms of kilovolt amperes. So that is the rating of a given transformer. So when we have a maximum efficiency, what will be the output kVA corresponding to that maximum efficiency is what we are going to study. So we know that whenever it is a we know that the efficiency, whatever is obtained, will be maximum when iron loss is equal to full load copper loss. That is Wi is equal to WCO. Under this condition, we get the maximum efficiency. So under this maximum efficiency condition, if X is the load we have considered, then Wi becomes the copper loss for X kVA output. That is, X is the load under this condition, that is under the maximum efficiency condition. Let us consider X is the total load. That is, under the load of X, we get the maximum efficiency. Therefore, what happens is WCU, that is copper loss, will be directly proportional to full load kVA whole square. We know that copper loss is always directly proportional to I1 square R1. That is directly proportional to the I1 square R1, that is full load kVA. That is the maximum load what can be obtained in the transformer. Whole square will be a copper loss. But we know that Wi is equal to WCU. So Wi can also be expressed as this full load kVA whole square. That is nothing but the capital X which is considered. So Wi will be proportional to X square. If I take the ratio of these two, Wi by WCU, it will be X divided by full load kVA whole square, or capital X will be equal to full load kVA into square root of Wi by WCU. So whenever we have maximum efficiency value, the load kVA rating corresponding to the maximum efficiency value will be obtained by, that is, this capital X is the load corresponding to maximum efficiency, which is given by full load kVA into square root of iron loss by full load copper loss. So this is the equation to find out the load, that is the kVA rating at maximum efficiency condition. So here we have written one more important thing, that is square root of Wi by WCU. This is nothing but the fractional load part. So when we talk about the transformers, always the transformers does not operate in the maximum efficiency, maximum loaded value. That is not for the full load condition. What is full load condition? Say for example, I consider the loading as 100%. That is the full load condition. So always the transformer will not be operating at a full load condition. So the reduced value of condition or the reduced value of load at which the transformer operates, it is taken as the fractional load condition, which is denoted by small x. So this notation can be different. It can be considered in different values. Here we are considering it as the small x value. So if I take the small x as the fractional load condition, so for maximum efficiency, Wi will be equal to X square WCU. So maximum efficiency, iron loss is equal to copper loss. So this, when iron loss is equal to copper loss, what happens is this X square is the value which is multiplied with respect to the copper loss, because it is a variable loss. This X is nothing but a fractional load value which is considered. So that small x fractional load value, whatever is there, it is always given by square root of Wi by WCU. That is, this x value is nothing but the load condition which has to be considered. Either it is 100% loaded or 50% loaded or 75%, 25%, how much ever is the transformer loaded, that load condition, that is the load value, will be given by square root of Wi by WCU. So by considering the full load condition or a loaded condition, the efficiency can always be obtained as, you can see here, this is the expression which will be used at any fraction of full load, that is at any fraction of the load which is there. When we calculate the efficiency, it is always given by eta x is equal to x kVA cos phi divided by x kVA cos phi plus Wi plus x square WCU. Always remember, this copper loss is a variable loss, so the load taken will also be a square of that, that is x square will be considered. So where x is a fraction of load, Wi is the copper loss, WCU is the Wi is the iron loss, Wc is the copper loss, and kVA is the rating of a given transformer. So this formula is used to calculate the efficiency at different loaded conditions, that is different fraction of full load conditions. So these are the some of the important formulas which has to be remembered when we solve some problems in the given transformer chapter.